It turns out there are multiple ways to specify hyponym-hypernym relationships. What we've done in this lecture so far is something known as interface inheritance. It's the type of relationship specification that I personally really like, and in the next video we'll talk about another one. So first, I'll tell you what interface inheritance is. And so it basically captures any time we specify the capabilities of a subclass using the implements keyword. That's known as interface inheritance. And to break this term down into its two words, interface in this case means the list of all of the signatures. So if we look at list 61b, these are all the things that a list can do. And then we use the word inheritance because we say that the subclass, the thing that says implements up at the top, it inherits that interface. So it's kind of like terms like, say, lock, right? So if you go to, I don't know, Amazon.com, let's say, and you search for locks, all of those locks have certain things in common. They can be locked, they can be unlocked. And there's no rule about how it works. Some of them use a key, some of them use a combination, whatever it may be. But the point is they can lock and unlock. That's the interface, okay? And each different example, A lists, S lists, padlock, combination lock, they have a different way of doing it. Okay, so it just says what the class can do, but not how. Now, in Java at least, the subclass actually needs to override all of those methods, right? Just as, I guess, on Amazon, if you tried to sell a lock that doesn't lock or unlock, it would probably be pulled from the shelves pretty quickly. In Java, if we have an A list that doesn't do something that it's supposed to, then it won't compile. Okay, so in other words, let's say we go and we modify the specification of list 61b so that I add a new method called pru. Okay, so this is a new thing that lists need to be able to do. Now, if we go back to A list at this point, we'll see that it no longer compiles. And actually the same for S list. They both don't pru, so they don't count anymore. Okay, so if we change the specification of list, then they won't compile. Okay, so it's very important that the subclasses override all of those methods. Okay. Now it turns out interface inheritance in the real world can get a little more complicated. We can have multi-generational interface inheritance where every list is also a collection, and this can actually go even further. We'll talk about that in a later lecture, but I just want to mention it here. Now, I am going to have figures like this a lot over the next 4 lectures, so I'll always have interfaces in white, and classes will be in green, though I might occasionally use a different solid color when necessary. Now, this notion of interface inheritance, it's an incredibly powerful tool that allows you to generalize your code because we're able to do things like write our word utils longest method so that we can find the longest item in an S list, an A list, or methods that haven't even been, or sorry, classes that haven't even been invented yet. Okay? So that's interface inheritance. Now, one thing that's interesting about interface inheritance is that while it's powerful, it seems to lead to a bit of a contradiction with things we talked about earlier. So way back in lecture 3, we talked about the golden rule of equals, or the mystery of the walrus. And a couple years ago, a student raised this particular problem with me. So the student said, hey, Josh, you said that when you say x equals y, or when you pass a parameter, you're just copying the bits. And secondly, Josh, you said that a memory box can only hold the address for something of the appropriate type. So you can't, for example, say string x equals new dog. And yet here, we have a longest method that is supposed to take in list objects. But whenever we call this function with, say, A1, which contains this is a 64-bit box that holds the address of an A list, somehow we're able to copy those bits, even though they're not quite the same type. This is A list, this is list. Well, the linguistic trick here is that when you specify an inheritance relationship, then, well, we can just say for short, an A list is a list. For all purposes that involve memory box checking, that's okay, right? The more maybe obtuse way of putting it is that if x is a superclass of y, then memory boxes for x may contain y. Or if we want to specify or substitute in something that makes sense, we could say if dog is a superclass of, say, poodle, then a memory box for a doghouse, can contain a poodle. Okay? And so therefore, if we have a list variable, it can hold a list addresses. Okay? So here's a question to see if that all made sense and bring together everything we've talked about with inheritance so far. Let's suppose we have a piece of code like this, where we say list 61b sum list equals new S list. And then we say sum list.add first elk. Which of the four scenarios here happens? 1, does it not even compile? 2, does it compile but it has an error here when we try and run this line? Is it 3, this line runs fine, but when we get to add first, it crashes because lists don't know how to implement add first, or 4, does everything work fine? So think about that question, and I'll spoil it in a moment. So pause the video perhaps. Okay, so let's spoil it. So I'll go to is a demo. I have a breakpoint already set here. And I'll first note that it is compiling. There's no red squigglies, so it compiled fine. It's okay. Now let's think about if we're the compiler. Well, the issue here is we know this is going to return, or the potential issue is we know that this is going to return the address of an S list, and it turns out that can go into a list memory box just fine. So the compiler is fine with it. Now when we actually try and run it, okay, so we open up the visualizer, we step over this line, and what happens is we create a list, and then we're able to put it in the sum list memory box. So this is a memory box that's 64 bits that holds the address of our list. Now when we actually try to execute elk, well, in this case, because the slist class overrides the list61b method that was specified under its list of capabilities, it'll work just fine. So it turns out the answer was D, everything works well. Elked well on existential crises. Okay, so here's our answer. All right, that's that. So in the next video, we'll talk about another type of inheritance, but make sure this makes sense before moving on, and I'll see you in that video.